Much for the introduction, and thank you for the organizers for allowing me to speak in this nice workshop. I hope everyone still has some strength to listen to the last talk of today. So I will be talking about work I have been doing for the last couple of years, starting from a paper we released last year during my PhD with Jan de Boer, Victor Korjanes-Kujaskivakkuri, and Jan is maybe somewhere in the audience. And so then I will continue on the project that we are now doing. So last year we also wrote a paper related to this on Virasoro circuits. I will mention something on this, but mostly I will be talking about this work that is to appear perhaps next month with my postdoc supervisor Johanna Erdmenger and Tim Schumann, who was a master's student in Würzburg and now he's doing his PhD in Ghent. Okay. So I will be talking about driven quantum systems, which simply put are quantum systems interacting with some external classical background fields. So they are defined by giving a time-dependent Hamiltonian, which is time-dependent in the Schrödinger picture, and takes this general form. So it's some linear combination of operators On with time-dependent coefficients lambda n of t, and these lambda n of t are just C numbers which have arbitrary time dependence and they're controlled externally. So they are these classical background fields which couple to the quantum system through these operators On. Now, why would one be interested in these driven systems? Well, there are examples of non-equilibrium systems which do not have well-defined ground states. And the time-dependent driving can generate novel phases of matter that would otherwise be inaccessible in equilibrium systems. And a lot of focus in the literature, and as far as I know also in experiments, has been on so-called Floquet systems, which are periodically driven quantum many-body systems. And in these cases, the driving is periodic in time with period capital T, so the classical background fields satisfy this condition. And to highlight some work, there's this paper from 2010, which gives a topological characterization of phases that can appear in these kinds of many-body systems. Now, perhaps everyone is familiar that quantum many-body systems in the continuum limit are described by quantum field theories, and in particular when these many-body systems are one-dimensional, some spin chains or lattice systems, then these quantum field theories are two-dimensional. And a particularly nice family of quantum field theories are quantum field theories in 2 dimensions, where one can make a lot of progress. And what I will be talking about in this talk are so-called driven inhomogeneous CFTs. And in these driven CFTs, this set of operators that I showed you on the first slide is infinite, and the operators coincide with the generators ln of the Virasoro algebra, which is an infinite dimensional algebra present in any 2D CFT. So it's the symmetry algebra of 2D CFT. And yes, so in recent years, these inhomogeneous CFTs have gained a lot of attention. So here's an incomplete list of authors that have been working on this, and especially a lot of focus has been on Floquet CFTs. Now, the purpose of this talk is to relate these inhomogeneous CFTs, which are usually written in the Hamiltonian formulation. We write them as CFTs in Kerr spacetime. And in this setting, the driving is provided by a time-dependent background metric in Lorentzian signature. So this kinds of related work goes back to the late 80s by Kukar and Torre and Varadarayan, where they studied 2-dimensional massless free scalar fields in flat space, but where you foliate the theory, where you slice the theory using different foliations. And then you study the unitary evolution generated by these foliations. And this setup was recently then revisited by Erdmenger et al. And then in the paper from 2 years ago, we gave a curved space interpretation of this, and the current work is a continuation of this paper. So I would like to highlight some subtleties. So state evolution in quantum field theories in time-dependent backgrounds is non-trivial. So in higher dimensions, already in free theories, it's known that given a general background metric, there doesn't exist a unitary operator that implements the evolution on a single Hilbert space, on a single Fock space. However, there exists a notion of generalized unitarity, which was shown in this paper from 2015 by Agullo and Ashtekar. It's often claimed that this problem doesn't appear in two-dimensional quantum field theories, which general quantum field theories, there's many papers which look at some deformations of free theories and so on by adding mass terms. But I'm not aware of a general proof. But however, because now we'll be talking about 2D CFTs, we will see this explicitly, that there always exists a unitary operator that one can write down, which generates this evolution implemented by the background metric. All right, so here's the outline of my talk. So I will start by discussing or showing you what is a driven inhomogeneous quantum field theory, and then I will explain how it arises by coupling a CFT to a background metric. Then I will discuss the entanglement entropy in this context in a curved background, and depending on how much time I have, I will also describe the holographic dual in 3D gravity. Yep.
So can you comment on this non-existence of unitary evolution operator?
Yeah, well, I don't know so much about it. What would I? Well, I can comment that what one would expect is that there exists a unitary U of t, which arises when you foliate your space in some curved background, and then this kind of the unitary evolution evolving in this space-time metric corresponds to acting with this unitarian state. But this is not true in these higher dimensional situations, that there exists a single unitary that acts on a single Hilbert space. But there exists this notion of generalized unitarity where you have multiple unitaries which map between Hilbert spaces at different times. So you need like a one-parameter family of Hilbert spaces instead of a single Hilbert space to realize this situation. So that's, I guess, the best I can say about it.
Sorry, so is the statement that the Hilbert spaces at different slices in a general metric are not isomorphic, but in CFTs they would be because of...
in 2 dimensions there's no problem, that's the claim, and in 2D CFTs no problem. But I guess one can say that one has kind of this bundle of Hilbert spaces over R. So instead of having a single Hilbert space, you have some vibration. That's the...
But is this because there is the metric is dynamical, or is...
No, so the metric is not dynamical, it's completely fixed background. Yeah. Yeah, this was a surprise to me when I heard about this. Yeah. No, so it's, I wouldn't say, yes.
So this is defined in this way, somehow, because otherwise it can be...
Yes. So you can quantize your theory in this covariant way where you solve the equation of motion, and then you find some basis in which you can expand your field operator. And this is, I think, the standard way, but then you can see if there exists like a Heisenberg picture where you act on field operators with these unitaries, whether you can reproduce those that you obtain from the covariant approach, and it doesn't seem to work in higher dimensions. Maybe we can discuss this in more detail later.
No, what I mean is that in any of these Cauchy slices is the same Hilbert space, so the same thing. You can put the identity, let's say. So you are asking something more about your unitary that is somehow mapping local operators to local operators. This is a point.
Mm-hmm.
Okay.
Yes, but if you want to represent these operators acting on a single Hilbert space, it's not possible. You can have different representations on different Hilbert spaces, and then it would work, roughly speaking. So, yeah. Okay, so it's not a problem for us, but I just wanted to, okay.
Silly question, just as a preview. One is expecting to be driving the system without pumping in energy somehow?
No, you will pump in energy.
And despite pumping in energy, the thing will be associated with living on a fixed background, which is time independent?
Which is time independent.
Or maybe I should wait.
So you can compute the evolution of the Hamiltonian, expectation value of the Hamiltonian, it evolves in time because of this driving.
Okay, thank you.
So the energy eigenstates depend on time. The eigenvalues, yeah. All right, so inhomogeneous CFT is defined by this Hamiltonian in the Schrödinger picture, where we have two smearing functions, nu and nu bar, which are 2π periodic in this phi coordinate, and then they have some time dependence. And then we kind of smear these stress tensors, which are just the stress tensors of the 2D CFT in the left and right moving sectors. So they are mutually commuting, they live in different tensor products. And so this stress tensor has this Fourier mode expansion in Virasoro generators, which satisfies this Virasoro algebra with central charge C. And this is an example of a driven quantum system, because if you expand this nu and nu bar in Fourier modes, you can write it in this way, which is now an infinite linear combination of operators of these Virasoro generators with these time-dependent coefficients. And so this study of these inhomogeneous CFTs began from this so-called sign-squared deformation in quantum many-body systems, which was introduced to regulate boundary effects. And then it was later realized that in the continuum limit in CFTs, which describe these systems near quantum critical points, this sign-squared deformation is a special case of a Möbius deformed Hamiltonian, which corresponds to setting nu bar equals minus nu and then taking this nu to be a cosine. So then the Hamiltonian is a linear combination of L0, L minus 1, and L1. And then time dependence to this was first introduced, as far as I know, by Xeda Wen and Wu in 2018 in the two papers, where they did time evolution with kind of a sequence of time-independent Hamiltonians. So it wasn't continuous time evolution, but it was this Floquet evolution. And then kind of this Floquet evolution, discrete Floquet evolution, was generalized to arbitrary inhomogeneities nu in these papers. Now, the state evolution, of course, in these closed systems is unitary and governed by the Schrödinger equation, which is this here, and this is the Schrödinger picture Hamiltonian. And now we can solve this to find that the state at time t is obtained by acting with u of t on the initial state r, where this unitary is a time-ordered exponential with this time-dependent Hamiltonian. And in an inhomogeneous CFT, the Virasoro algebra allows us to compute this u of t explicitly. So if we plug in the expression for the Hamiltonian I showed you, we get this expression for the unitary. And now it's useful to introduce these two one-parameter families of functions from the real line to the real line, ft and f bar of t, which satisfy these constraints. And then without loss of generality, we can parameterize this smearing function nu bar in this way, where dot is derivative with respect to t and prime is derivative with respect to phi. And then we also assume this positive derivative condition. Now, these functions define kind of curves as a function of t under Lie group diff S1, which is the Lie group of diffeomorphisms of the circle, given by these kinds of maps. And this f prime being positive means that they are orientation preserving diffeomorphisms. And now, on the Hilbert space of the CFT, given this diffeomorphism little f, which is the inverse of capital F, this diffeomorphism is represented by a unitary operator, which has this time-ordered exponential form. It's represented by a unitary operator because these FTs, they correspond to conformal transformations, which are symmetries of the CFT, to summarize it very quickly. And now one can show that these unitary operators form a projective representation of diff S1. So if you take a product of two unitaries, you get the unitary corresponding to composing two of the diffeomorphisms, but you get it up to a phase. And this phase is also well known explicitly, and it's called the Thurston-Bott-Tuco cycle. And equivalently, one can think of this V as a unitary representation of the Virasoro group, so not as a projective representation, but an ordinary representation, and this Virasoro group is the central extension of this diff S1. So now in a inhomogeneous CFT, this unitary operator factorizes into this tensor product of projective representations of diff_1. And this kind of unitary is known as a Virasoro or conformal circuit. And one can study the circuit complexity of these kinds of circuits, which was initiated by a paper by Nielsen from 2005. And the circuit complexity of these Virasoro circuits was studied by Caputa Maga and Florian Heller. And then in this paper from last year, we also looked at this again. So that's not directly related to this talk. Okay, so now I'll explain how this can be obtained from curved backgrounds. So there has been various works in the past which have related inhomogeneous CFTs to CFTs in curved spacetimes in some form. So the first one was this paper from Tada from 2014, where he discussed the sine squared deformation. And the general case was worked out in this paper by us from 2 years ago. However, this is full of subtleties. So the curved space calculations, if you want to relate them to the operator formulation, is tricky, and we didn't cover all the details in this paper. So the purpose of the present work is to address these subtleties in a Lorentzian framework. And in particular, why this took us quite a while was because most of the literature on 2D CFTs in curved backgrounds is in the context of worldsheet string theory, which is in the Euclidean signature, which doesn't directly translate to this time-dependent Lorentzian setting. So the setup is as follows. We consider a cylinder with a coordinate phi parameterized in the spatial circle, and then we have the time, and we equip this cylinder with a Lorentzian metric G. And in 2 dimensions, any metric can be parameterized by 3 functions of the coordinates phi and t. And these 3 functions are omega, nu, and nu bar. And the metric can be written in this way. And then again, with a loss of generality, we write the functions nu and nu bar in this way as before I showed you. This is not a coincidence, they're related. And then one can always define these light ray coordinates, which are functions of t and phi, by this expression. And then in this coordinate system, this metric G takes a conformal flat form where the Weil factor is omega plus var phi, and var phi has this expression. Now, to define a CFT in a curved background quickly. So if we consider CFT on a curved manifold, MG, there's some fundamental field, and then it's defined by this action. And on these fields, phi and the background field G, there acts a group, which is the group of diffeomorphisms and Weil transformations, or diff cross Weil, which has elements, pairs of diffs and Weil transformations, such that the metric transforms in this way, and then the fundamental field transforms in this way. Let's say here it's a rank n tensor field, and then this delta phi is some Weil weight. But the point is that the classical action of the CFT is diff cross Weil invariant, so it satisfies this equation. And important point here is that this manifold M is also pulled back by the diffeomorphism, and this makes a difference if the manifold has boundaries, because the boundaries are moved by the diffeomorphism. Now, given this action, we can write down the classical Hamiltonian of the CFT. So it can be defined as this Hamilton-Jacobi variation of the on-shell action. So we consider this finite section of the cylinder between this Cauchy slice t equals 0 and the t equals s. And then we, in this section MS, we solve the scalar field or whatever fundamental field equations you have. So this doesn't rely on what is the exact theory. You find some solution phi of s, and the solution depends on this location of this final boundary, because by the boundary condition that you impose there. So you impose boundary condition that equals 0 and equals s, and you find the solution, and then you compute this on-shell action. And then you can show that diffeomorphism invariance implies that this Hamiltonian can be written as an integral on the Cauchy slice of this form, where this TAB is the classical curved space stress tensor of the CFT, and gamma is the induced metric on the constant time slice, and T is the unit normal vector in the time direction, and Xi is also parallel to the unit normal vector, but it's not unit normalized, and this Xi would be the killing vector if the background metric was time independent. So this is the starting point, and upon quantization, this stress tensor is promoted to the classical stress tensor is promoted to a field operator, and this promotes the classical Hamiltonian also to a Hamiltonian operator. But then there's the following question: is this Hamiltonian in the Schrödinger or in the Heisenberg picture? So in other words, the Heisenberg picture Hamiltonian is given in terms of the Schrödinger one by acting with this unitary, where the unitary is the time ordered exponential of either the Schrödinger or the Heisenberg one. It doesn't. This is a mathematical identity. You just reverse the time ordering there. So the question is whether the classical Hamiltonian goes to the Heisenberg one or to the Schrödinger one when you quantize the theory. Of course, now I'm talking about quantizing some free theory with fundamental field, but this discussion generalizes to strongly coupled CFTs as well. But so I claim that the answer is the Heisenberg Hamiltonian. And one way at least to see this is from the fact that the classical stress tensor satisfies the on-shell diff cross Weil-Ward identities, which is the conservation equation and the vanishing trace, which is very familiar in 2D CFTs. And the point is that you can write this conservation equation as in this way if you use the metric I showed you before. So you get some time derivatives acting on this classical field, which this combination here is promoted to a Heisenberg picture operator. And then these conservation equations become the Heisenberg equations for this Heisenberg picture stress tensor. So that's the reason why we get the Heisenberg Hamiltonian. And then there's some more subtleties, which is related to the UV divergences. So the stress tensor, of course, when you start from a free theory, it's a composite operator, and it has UV divergences, which have to be renormalized. And this gives you a renormalized stress tensor operator. So now, without referring to any CFTs, we can claim that the renormalized stress tensor satisfies renormalized Ward identities. And they break the diff cross Weil symmetry by the conformal anomaly. This is well known. So one can compute this in different renormalization schemes. And in the differmotion invariant scheme, the conservation equation is preserved, but the trace of the stress tensor picks up this Weil anomaly. So the Weil symmetry is broken at the quantum level, but the diff invariance is preserved in this scheme. So this is completely general, which can be derived by general arguments. But what is less well known is that there exists another scheme, which we call the Carrelli split scheme, in which these equations kind of take the following form. So now, in this scheme, the renormalized stress tensor has vanishing trace, but there's a violation of the conservation equation. So you get some differmorphism anomaly on the right-hand side of the conservation equation. And these are now equations that one can solve for the renormalized stress tensor operator. And you find that in this scheme, this is the solution for the components. And here, sorry to mention, this minus, minus, and plus, plus are components in the light ray coordinates. And so here the first term is some operator, which depends only on x minus and x plus. And this is quantized in the usual way in terms of the two copies of the Virasoro algebra. So there will be two commuting copies. But what is non-trivial is that now this diffeomorphism anomaly leads to these Schwarzian terms in the renormalized stress tensor with the Schwarzian derivative. And what is unusual here is that these Schwarzian derivatives only involve derivatives in the phi spatial direction. And one can also show that this same result for a free canonical quantized scalar field can be obtained by doing point splitting in space, which is different than usual point splitting descriptions that were described in the 80s in different contexts. All right, so the point is that you have this renormalized stress tensor operator, and this coincides with the Heisenberg stress tensor operator. And this implies that the Heisenberg picture Hamiltonian in Kerr space takes the following form. And the important thing here is that you have these Schwarzian terms which lead to basically a changing energy expectation value as a function of time due to the driving. And then the Schrödinger picture Hamiltonian Kerr space takes this form, and this is exactly the form of the Hamiltonian of an inhomogeneous CFT that I started with in the very beginning. So this shows you that the CFT in Kerr spacetime matches with an inhomogeneous CFT. And this also implies that the driving in the curved background generates a unitary operator of this form. So indeed you get the unitary operator in 2 dimensions in this case. And you can also understand now how this conformal anomaly appears in this operator formulation of the theory. So basically it arises from the fact that if you start from a time-independent Schrödinger picture stress tensor, you have to, when you got the Heisenberg picture, you act with the unitary U, and what you get is by this standard Schwarzian transformation law of the stress tensor, you generate this Heisenberg, you generate this Schwarzian term. So basically the conformal anomaly appears in the chirally split scheme due to the difference of Schrödinger and Heisenberg pictures.
So can I ask a question? In the usual 2D CFT, this is like when you go from the plane to the cylinder, the conformal anomaly appears in precisely the same way.
Yeah, so here we are just on the cylinder, but in a curved background.
Right. No, so is there a way to understand this in terms of a cylinder to plane mapping? Because it looks like literally the same equation. No,
so if you do the cylinder to plane mapping, you only generate a Casimir energy, which is a constant. Yeah, let me go to the next slide. Maybe it will become clear here. So if you want to compute the expectation value of the stress tensor, so you can either compute it in the Heisenberg or the Schrödinger pictures. They are of course equal. And then what you obtain is that in the vacuum state, you get this Casimir energy, and this is the one you would get if you did the map from the plane to the cylinder. But then from the curved metric on the cylinder, you get these extra contributions to the driving. So the Casimir energy is modified the driving, and this can also be reproduced from holography up to some subtleties, which I don't know if I have time to discuss, but we will see. Now, a couple more comments. So this diffeomorphism invariant scheme is controlled by the so-called non-local Polyakov effective action. So this one reproduces you a stress tensor which satisfies the Weil anomaly equations, so the diff cross Weil word identities. And the chirally split scheme is controlled by 2 copies of the Alexei-Satasvili actions. And these 2 effective actions are related by counterterms, which are finite, and they are local in the background metric, so you are free to add them. And this is kind of like a Lorentzian version of a story from worldsheet string theory, where this issue of factorizing this Polyakov action into left and right moving sectors, which only involve the Beltrami differential mu and mu bar independently, was called a holomorphic anomaly. And this one was studied in the late 80s by both Verlindes and then Hermann. All right. So now to discuss some computables. So for the entanglement entropy, this is the setup. So we consider some interval and a constant time slice with endpoints phi1 and phi2. And then on the cylinder, we have this curved metric G driving the evolution. And so I guess Norte Christian already kind of explained how to define an entanglement entropy, but I will redo it here. So the reduced density matrix of this interval in the global state generated by the background metric, by the driving, is obtained by tracing, taking the trace over the complement of the interval in this instantaneous state. And then the entanglement entropy is defined just as the von Neumann entropy of this reduced density matrix. But alternatively, it's easier to work with this quantity, which is the nth power of the reduced density matrix, where n is an integer, and then one can compute this trace for integer n, analytically continue in n, and then take this derivative and take n to 1, and then you should end up with the entropy. So this entanglement entropy is UV divergent due to the infinite entanglement that across the endpoints of the interval. So therefore it's also scheme dependent. And so in curved backgrounds, if you want to calculate entanglement entropy, we can use the replica trick in Euclidean signature, which was introduced by Kalapris and Cardi. And now we had this Lorentzian driving situation, and we want to do a Euclidean replica trick calculation, so we have to find some analytic continuation. And the way to do this is to analytically continue in this light ray coordinates x minus and x plus. So if you try to analytically continue in T, you get the complex metric, so that doesn't work. So this amounts to basically looking at the cylinder equipped with the Euclidean metric of this form where you have some Weil factor sigma e, and then when you analytically continue the imaginary part of W into the imaginary axis, you will get back this Lorentzian metric that we used for the driving. Now, to calculate the entanglement entropy, the replica trick basically instructs you to look at path integrals over the so-called replica manifold Mn. And these Euclidean path integrals are defined in this way, where we have the Euclidean action. And this is what the replica manifold looks like. So as Christian explained this morning, you obtain it by cyclically gluing n copies of your cylinder across this cut that you slice on this along this interval. But here the non-trivial thing is that this is in a curved background, which means the following. So there's this called a map P, which is a ramified map that maps this replica manifold into a single cylinder, and it's an n-to-1 map because it maps these n sheets to a single cylinder. And now on this single cylinder we had this Euclidean metric GE, which was the curved metric, and that gets pulled back on this replica manifold into this metric P star GE. So that's why we have to compute this kind of Euclidean path integral. And for this, we can use some recent results from early this year, where this kind of path integral was computed using the Liouville action by Estienne and Lin. And they treated especially carefully the following problem, which is that this Liouville action of this manifold, replica manifold, is UV divergent, and one has to regularize it by cutting holes around the entangling points. So this will also mean that these UV divergences that you have in the Liouville action correspond to the UV divergences of the entanglement entropy. Okay, so if you do this calculation, I claim that this is the final answer. So the entanglement entropy in a different invariant scheme, so because it's a UV divergent quantity, there's a choice of renormalization scheme. And this is the usual scheme, which gives you the Weil anomaly and preserves different invariance. So what you find is that the entropy that you obtain depends on the Weil factor of the metric at the endpoints of the interval. So that gives you time dependence. But then you also have this dependence through this ft5 functions. And this means that this entropy knows about the full history of the driving, because these functions ft and f bar of t are non-local functions of the metric, because basically it was f dot which gives you the metric. So if you want to solve for f as a function of the metric, you have to solve this first order differential equation, and then to solve the first order differential equation you have to integrate over the history of the driving. Yep. Yes.
Bottom half of the cylinder is equal to this reflection in time, right?
There's no, yes.
And here you have a time-dependent Lorentzian situation. So how they match each other? Because
because you do the Wick rotation in the x minus coordinates. So it's only thing you're doing is you're replacing this Weil factor here. Sorry, which is a function. It's a map from R cross R to R. You're replacing it with a map from C cross C to R. And then you just choose this sigma in appropriately that you get this function. So it's kind of nice that it works. But if you try to Wick rotate in t, then there's no reflection symmetry in the t coordinate because the metric is time dependent, and then it doesn't work.
Okay.
And okay, here this epsilon1, epsilon2 are the cutoffs. They are radii of the two geodesic disks that you cut around the entangling points, and they are geodesic as measured by the flat metric. So not by the curved metric, but by the flat metric. And now this result matches with previous results in special cases by Holtze and Larsen and Wilczek from the early 90s. And also this Weil factor dependence matches with this paper by Shaposhnik, for example. People have studied how entanglement entropy transforms under Weil transformations of the background metric. And this also matches with the holographic calculation using the Ryu-Takayanagi formula. However, it has a problem that this Weil factor dependence is incompatible with the state interpretation. So why is that? Well, the state at time t is obtained by, let's say, starting from the vacuum and acting with a unitary operator, and this unitary operator is a time-ordered exponential of the Hamiltonian. And the Hamiltonian doesn't know about the omega. That's the property of the CFT, it's a property of wide invariance. So this means that the state at time t doesn't know anything about omega. So how can the entropy depend on omega? Because it's a property of the state. So that's the incompatibility with this expression. But the solution is that we computed this entropy in the wrong scheme. So the correct scheme to compute it is the Carrel split scheme, and in this scheme you basically add finite counterterms which exactly cancel this omega dependence, and you're left with this expression. And this is the expression I claim is the correct entanglement entropy in the curved background. And this is also consistent with some previous literature where people were computing entanglement entropies using twist operators. And the operator algebraic derivation of this formula is something we are trying to understand because it's less clear. So I guess I still have some time to talk about the holographic dual of this. Are there any questions? Yeah.
How would you explain that that Carrel split scheme gives you a right answer while a diffeomorphism invariant, which seems to be preferable in quantum field theory, gives a wrong answer?
I don't know how can I answer why question. That's from the point of view of canonically quantized scalar field, there's a natural answer in the sense that you can do this point splitting, and then this point splitting gives you answers which match with the Carrel split scheme, but which do not match with the diffeomorphism invariant scheme. And another reason why, I guess, is that classically the trace of the stress tensor vanishes. And if you quantize the theory, you always get something which is on shell. All the field operators are on shell, so then there's no t minus plus component. Yeah.
It's usually people believe that there are some basic invariances like gauge invariance and diffeomorphism invariance, and you allow anomalies in Weil transformations and in Carrel transformations. However, you kind of advocated just the opposite point of view.
Yeah, I mean, I'm saying, well, I mean, I don't think there's any tension here. It's just that you have the operator formulation which gives you the anomaly in another scheme, but the fact that you can add some finite counterterms to get a diffeomorphism invariant result, that's kind of non-trivial, and maybe that tells you something that in nature everything has to be diffeomorphism invariant. I don't know, but it's, yeah, I would say it's a choice in the end. Yeah. They come, yes.
They disappear in any well-defined quantity. So it's like in the mutual information they will cancel. So it doesn't.
Well,
it's kind of
it depends. Well,
cutoff thing, right?
Well, I mean, if you compute mutual information or relative entropy, I would expect that this dependence on the cutoffs cancels, but you're left with these finite terms. So basically, one way to see why this dependence arises is that in a curved background, you can define your cutoffs in a diffeomorphism invariant way. So your cutoffs depend on the Weil factor, and that's why you get this dependence. That's the usual argument that to get entropy in curved space, you start from entropy in flat space, and then you just redefine your cutoffs. Because now, if you're an observer, you can only measure geodesic.
Your cutoff as you want. Then you have to subtract to eliminate the cutoff or something like that. Right? You have to do another calculation to eliminate the cutoff. So I was asking if these omega terms are the one that you want to eliminate, right?
Yes.
And these are somehow local at the endpoints, yes. So there is no problem with those.
Yeah, but the thing is that also these are local at the endpoints. So you can think of this as being a log f prime on top. But these are the things which usually arise from the transformation of the twist operators when you act with the Virasoro representations on them. So this is the usual term. But so you want to only get rid of this one, not of these ones. So it's a bit subtle how to do it.
I think both of them will disappear in physics.
Yeah. But the point is that, like, if you think about entanglement generation, So if you want to subtract the difference of two entropies, like some mutual information, these survive, and people have used this dependence on the Weil factors to say that in curved expanding universes you have entropy production. And it seems to come only from the cutoffs, that you change the cutoffs in a curved background. Yeah. Yeah. Okay, so the holographic dual of this 2D CFT, at least in the bottom-up models, is a 3D gravity. And so we can introduce a 3-dimensional coordinates with Pfeffer-Graham coordinate z, and then we have the boundary directions. And we would like to find a solution of 3D gravity which describes this driven CFT. So what you want is that you have a 3-dimensional bulk metric, which when you take the Pfeffer-Graham coordinate to the conformal boundary, you get this metric that drives the CFT there. And to find this kind of solution of 3D gravity, it's simplest to start from a well-known solution, which is, I think the battery is dying from the laser pointer, is to start from the Poincare ADS metric and act on that with the diffeomorphism. And because Einstein's equations are diffeomorphism covariant, you get another solution in this way. And to find the correct solution with the correct boundary condition, we can use a diffeomorphism which was found this year, which is this one. You can write it in the following way, where you have this covariant derivative, where this sigma plays the role of a connection, and then plus minus mean derivatives in the light ray coordinates. And then here also you have a map, which is this map that maps a cylinder to the plane. And this is needed in this diffeomorphism to ensure that you reproduce this Casimir energy in the flat space correctly. So if we act with this diffeomorphism on the Poincare metric, this is the metric you get, and this is also a locally ADS metric everywhere. It has a truncated Pfeffer-Graham expansion, as you expect from solution of 3D gravity. It gives you the correct metric on the conformal boundary, and then these subleading terms in the Pfeffer-Graham expansion G2 and G4 are given in terms of the boundary metric, so in terms of sigma, which is the Weil factor, and then also in terms of this map from the plane of the cylinder, which is Schwarzian of that, which is just C over 12. And G4 is given in terms of G2, as a product of G2. And this is now valid for arbitrary driving, which generalizes the previous results we found. And people have been using these kinds of metrics to study how the horizons in the bulk evolve due to the driving of the CFT. Now one can also use this geometry to compute entanglement using entanglement entropy using the Ryu-Takayanagi formula. And that basically says that states that entanglement entropy is given by the length of a geodesic in this solution dual to the driven CFT. So L tilde is the length in this metric G tilde, and this geodesic is attached to the endpoints of the interval on the conformal boundary. And we can of course find this geodesic length using the geodesic length in the Poincare disk geometry, because the metric G tilde was just the diffeomorphism, and the geodesic distance transforms also, a geodesic length also transforms as a biscalar on the diffeomorphisms. And what we find is that the Ryu-Takayanagi formula gives you the entanglement entropy in the diffeomorphism invariant scheme. And this is expected since Einstein gravity reproduces the conformal anomaly in the diffeomorphism invariant scheme. So it reproduces you the Weil anomaly. And gravity always preserves diffeomorphisms, so this is natural. But if we want to find this Carrel-Spitz result, we have to add a boundary term to the Einstein gravity action, which is basically the counter term that takes one from the diff invariant scheme to the Carrel-Spitz scheme. And those terms in the Einstein action then reduce to boundary terms to the RT formula, which would cancel this omega dependence. So this I will skip. Okay, so to conclude, we showed that an inhomogeneous CFT is just a CFT in Kerr spacetime. And the Kerr space anomalous for the identities amount to Heisenberg equations for the renormalized stress tensor operator in the operator formulation. And the operator formulation produces the conformal anomaly in the Carrel-Spitz scheme, but you can always go the diff invariant scheme by adding extra counter terms. And the Kerr space entanglement entropy has a state interpretation only in the Carrel-Spitz scheme. And then we also derive the holographic dual of this setup. And some future directions. So the first thing that comes to mind is to introduce possibly moving boundaries to this setup, so basically driven B CFTs. And then, because we have here a general choice of background metric that drives the CFT, it would be interesting to look at how the driving is implemented by two-dimensional black hole backgrounds. So this is something that is recently been looked at by Stephen Giddings. Then we would also perhaps introduce driving by additional matter fields, which is something we did in this paper, but we didn't look at it from the CFT point of view, but just studying kind of these unitary circuits. And one could introduce driving with k dV charges, and then of course we would like to understand this entanglement entropy issue more precisely. Thank you.
We have time for a couple of questions.
Hi, Jani. Thank you. Very interesting. Have you considered two intervals in holography? The reason I ask is essentially just catching up with Horacio's question. If you had mutual information, you could see which terms drop out and which not.
Sorry, the quantum mutual information in holography?
Yeah, compute mutual information in holography. For two intervals, I just...
Yes, so no, we haven't considered that, but it would be interesting. Yeah.
Okay. Would it be in that? I mean, I guess it's just computing geodesics in AS3.
Right. Yeah.
Just I don't know how difficult.
Yes.
Other than it's precise, more common than the question.
Yeah, we can discuss it.
More questions?
From the other half of the auditorium?
Okay, I guess not. So let's Jani again.
Thanks.